It aligns with the industry's mission of safety through reliability. And our speaker, Kartik, he's been with Ford Motor Company. He works in quality of the underbody. He's a Six Sigma Green Belt for Ford, as well as a Design for Six Sigma individual. And maybe sometime we'd want to come have him back to talk about DFS. That was a really hot topic not all that long ago.
Yeah.
But 18 years of experience in automotive technology sectors, and his role is warranty commodity engineer. Does that sound right, Kartik? Anything?
No, I guess that pretty much summarizes everything.
Yeah,
okay.
I just wanted to give a brief little introduction.
Yeah, I do have a similar introduction in my slides too, but yeah, that's fine. Thank you.
It's taken right from your information, correct?
Yeah.
So, Kartik, you are now.
So we're ready to go.
You should be able to share.
Okay.
We are recording.
Window entire screen. Okay. Should I select entire screen? Okay. Okay. Let me know when everybody can view my screen.
Coming through.
Okay.
Yep, got it.
Okay. So first of all, I really appreciate this opportunity. This is like the second time I'm speaking on this topic. It's one of my favorite topics, and I've tried to summarize and kind of try to not minimize the content, but try to optimize it and see how much I can. I want to convey some important information, and I want to make sure that that information is conveyed in the 40-45 minutes that we have. This is a very vast topic. I will try, and I'm open, like at the end of the slideshow, you will have my email. Please reach out to me for any feedback that you have or something that I can help on. If you need assistance regarding some optimization that you're looking for, I'm more than happy to help. So with that, let me move on to the next slide. This is just a few minutes I'm going to spend just based on just talking about my experience. So I started my career with Infosys Technology Consulting, and then I've worked with Adient Seating Systems, Magna Seating, and then right now with Ford Motor Company. At present, I'm at Ford Motor Company as a warranty commodity engineer, and my role is more about delivering the major savings and driving some continuous quality improvement objectives. My other areas of expertise include warranty part analysis, root cause analysis, and also cross-functional problem solving. Now, I was I added this last statement at the very end just before starting this meeting. Is Infosys Technology Consulting was where I was first exposed to this whole knowledge-based engineering field. It's a very vast field, and that's when I really saw firsthand how knowledge-based engineering can help optimize very complicated systems. When I first was told that I'll be part of this team, I did not have any clue. But as I learned the tricks and as I kind of learned what it is and how it's applicable, I kind of see this application almost everywhere, in automotive, in aeronautical, in every domain that has manufacturing, or every domain that has complicated engineering. We can definitely use knowledge-based engineering. With that, I will go on to the agenda, which is kind of self-explanatory. I'm just going to briefly go through the introduction and then go through what is knowledge-based engineering, what's the role of AI in the automotive reliability. So I'm kind of splitting the whole topic into two different parts. I'm going to first talk about what is just KBE or knowledge-based engineering, and then we're going to talk about AI, and then we're going to see how AI and knowledge-based engineering can be merged or can go hand in hand to further optimize the automotive field. And then we're going to go through two real world examples, which will hopefully try to send the message and hopefully give a picture of this whole topic. We're going to go through implementation, like based on my experience at different companies when we have tried to implement any of the knowledge-based engineering, either a software code or it could be a set of instructions. What are the roadblocks that we have faced? And I'll also, if we have time, spend a few minutes on how we can overcome those roadblocks. And then the last few minutes is open question and answer. And hopefully, if I don't get the time to answer everybody, surely email me and I will definitely try to answer. So far, so good. Okay. So,
Yes,
what
sorry.
is
Yeah, loud and clear, coming through great. Thanks. All.
okay, great. So, what is knowledge-based engineering? So, very, I think this whole domain started somewhere in the 60s, especially I think uh, Airbus Aeronautical Company, the one that makes the aircrafts, they were one among the first companies uh, that that highly implemented, very successfully implemented knowledge-based engineering systems, and they kind of still continue to do so. And then once the company, the scale of Airbus, once they started to look at how they could optimize, and they saw through the gains that they made in terms of manpower, in terms of the time saved to do a particular activity, that's when a lot of other industries also started implementing it. Uh, NASA was the other big organization that has successfully implemented a lot of these knowledge-based engineering systems, and it's then gone down to Ford and all other automotive companies. So if you ask me, if you're hearing this term for the first time, KBE or knowledge-based engineering, what it in a very simplified manner means is that the the engineer who's working on the system need not know everything or need not really have to do all the work on his own. What KBE is doing is it kind of wraps you. So just think of this as like a wrapper on top of a bunch of rules, regulations, and precision logic. So you feed an input, it goes through the input and it spits out an output, and that output is what is essentially useful for the end user. Okay. It kind of automates routine engineering tasks. So the end user, if I am the user, if I'm working on a bunch of engineering drawings, I don't really need to remember and work on routine tasks that kind of eat my time. They kind of uh, I lose focus on what is essentially required for me to do in engineering. So these tasks can be automated, and the biggest advantage is that it reduces the human error, and it standardizes things. So for instance, if I have to give you a very simple example, I'm quite sure most of us on this call right now have used a lot of the computer aided design softwares like Unigraphics or Ideas or CATIA or of the so these packages, these softwares have inbuilt knowledge based engineering APIs, or I would say like simple simple code that we can just use to automate routine tasks. And um, I'm trying to simplify it and explain it in a very simple manner, but the application is so infinite, and you will see those real life examples as we go through these things. Is if you take a simple engineering drawing, Ford has its own set of corporate drawing standards. They all follow the ISO standard, but they also have some corporate standards, which could be as simple as like the font size, the font size of the text, the font size of the numbers, where the views in the drawing system are labeled, etc. All those standardized tasks don't need the engineer who's working on it, he or she, they don't need to remember all this. They don't, because all of these rules are standardized. So all you can do, if you can visualize the system, if I'm working on a drawing, all I need to do is just hit a simple, like click on some icon, and it immediately automates the task, and my entire drawing is standardized to meet the Ford drawing standard. So your time and effort is focused more on the engineering aspect of it rather than just doing the routine tasks. It's so this is KB in a very layman terms, and now we are going to go to the next slide, and we're going to see as to like why do we and AI, artificial intelligence, as you have heard and as you have seen, a lot of us have started to use AI in our day-to-day life. It is a tool that basically can think for itself. So it's a tool that can use what you have already done and kind of read, compare with the other users' work, kind of summarize it, and also the predictive analytics is where AI really is the game changer. We will go more into that, but so uh, most of these rules are most of the points that I've mentioned here are like kind of self-explanatory. Is that AI brings the pattern recognition, and it also brings in the predictive capability. Now KBE brings structures, rules, and domain expertise. In mechanical engineering, or with any form of engineering, there is a lot of physics and math involved. The end user needs to have an overall view of what that math or what that science is doing, but if the calculations are repeated, and all you have to do is feed in an input, and an output is spit out, then why not use KBE? So the first point, AI brings a pattern recognition. The second point is that the KBE brings structures and rules. Now, when you mix both, when you do 1 plus 2, the third point, together, AI can plug in the predictive analytics. It can think for itself. It's one more brain that can think, and it can proactively do the risk detection and also flag, so the end user need not really remember all the math in his mind and do all those hand calculations. Like, since I've worked on seats extensively, and if we have somebody in the seating expertise right now on the call, you will know when you're working with seat structures, there are so many mathematical calculations with respect to the force and impact, and then the impulsive force, etc. All of that can be kind of wrapped into a KB application. So all you need to do is just click an icon and you get the output. Now this is where the magic happens, is when you combine the two. That is when your entire product life cycle is extremely accelerated. We have already seen some real life examples. I'm going to talk about two of those later in the slide. But just think of this as a software program that is run by an AI. Now here we're going to be talking about AI capabilities applied to automotive reliability, as I mentioned on the slide. So I didn't want to write a lot of notes on this slide and confuse people. I have just written just to summarize the 3 or 4 major points that I wanted to talk about, and I'm going to speak on those points. So since I work as a warranty commodity engineer in my field, we very frequently look at claims. We look at hundreds and thousands of claims that a particular vehicle or a particular component has accumulated. When I say claims, those are actual failure modes or actual ways in which the part has failed under different geographical or different driving conditions, and some user somewhere in Austin or somewhere in Florida has not been happy with the particular component and has flagged the component. He has got it repaired. Now that when that part gets replaced, what is it speaking? What is that part really trying to tell? That is where the AI can help recognize the failure modes, the failure graphs, and it can help in identifying the reliability risk very early in the cycle, very early in the design cycle. I can't mention how many times it has happened that the a particular component has been accumulating hundreds and hundreds of claims, and it suddenly comes to the notice of engineering, because all this while nobody really paid attention to all the claim data, which is actually speaking to you about the early failure modes that we are seeing in the part. The faster we come to know those failure modes, the faster we can fix them, and the faster that we will see that the overall quality index of the vehicle can improve. And then, when it comes to component degradation, now this is an interesting point here, and I'll the main, how to explain it is basically, if you are seeing components that, if there is a CAD for a particular component, and when we are designing and engineering the part, we choose the material based on certain aspects of engineering. We look at the load path, we look at historical failures, and then we try to learn from the older model year vehicles as to like what could have failed in the older model years that we can learn and implement in the newer model years. Now that is where, if you have an AI-based, knowledge-based engineering system integrated with your CAD software, as soon as you are designing, it immediately flags when you do not follow certain design standards, or when you do not design the part that learns from the previous failure modes. What I mean to say is, if you're designing, let's say, a simple plastic component and you're making ribs on the component, there have been numerous instances when those ribs have not been designed the as per the standard that they should be. So what happens is down the line, you're going to have manufacturing defects, you're going to have strengthening defects, you're going to have components that really do not function as intended. You're going to have parts that actually break down in the field under extreme heat or extreme cold. Now, AI can look at the predictive failure modes from the previous model years and all of this and implement that knowledge. And as soon as when you're designing the component on the CAD software and you start designing the ribs, you will get it first time right. As soon as the ribs are not designed as per the standard, it flags it. It shows you that, hey, your rib pattern is not meeting the standard. In model year 23 or model year 24, a similar rib pattern was done and it failed to keep the part strong, and we had a number of failures. So that way you can mitigate the risk. And the third point is automated rule generation from historical data, which is what I just explained. Is like it's going to look at the failure modes from the past and try to learn into the future. Intelligent design optimization. Why this happens is because you will be able to make faster decisions with fewer manual steps. It will give you immediate feedback on what is passing and what is failing. It will give you the recommended improvements. So the CAD software immediately will show you the recommended improvements. It will minimize the repetitive work required for you to optimize and come up with a good optimal design. So instead of 20 steps, you can do this in 3 steps. And that time can be focused, whatever time you're gaining can be focused on deeper problem solving. Every company is facing this crunch, is that you want to do more with less. So AI integrated with knowledge-based engineering can really help shorten that cycle required to optimize. This is pretty much very similar. I think I have walked through most of these points. I should have come to this slide just before talking, but I've gone through most of these things. Is like early detection of high risk design elements. Airbus uses a lot of knowledge-based engineering in their wing designs. There is a lot of physics and math involved when it comes to the fluid dynamics and how the wing should be optimized, and almost 60% of their wing design is highly optimized. It's all because of the knowledge-based engineering. And the other example that I can think of is when it comes to the oil and gas industries, when it comes to certain standards that they need to follow for when it comes to the oil rig and the oil mining. I don't have real life examples. Maybe I should have added those, but a lot of the offshore oil rigs and a lot of those processes are highly automated. Because it's such a high risk job and it is also extremely prone to severe weather conditions. The whole intention is to reduce the manual effort, give the time back to the engineers to do better problem solving, and to take away the repetitive tasks into this. So just want to we are like kind of halfway through. I just want to take a pause and check with the team as to like how is the speed and are we all good?
Sorry, Kartik, I'm watching the chat for questions. I got a thumbs up so far.
Okay.
Couple of introductions. We have 40 people total on right now, but I don't have any questions or comments, and slides are coming on through. Your audio's great.
Okay, great. So I will that's just a feedback for me. I can just keep going on and on. Just want to make sure that I get through what I want to inform the team. Okay. Now, I know in the very beginning, in the very introductory slide, I had mentioned a point about safety through reliability. That is one of the key aspects, or that is one of the key themes in a lot of the companies nowadays. Is we are looking at how legacy systems are not really able to uh, take the work, not just the workload, but just the supply demand nowadays is so high that most of the systems have to be 99.9% accurate all the time. It would be better if they're 99.99% accurate, but the output that is really expected out of the systems nowadays is extremely high. So safety through reliability has been a very big theme in a lot of companies. I've been to one or two local uh, conferences among the automotive suppliers, and this is a very hot topic, is how to ensure that the components provide the required functional safety and are also highly reliable, which means to say how can the suppliers supply these parts and also keep the cost down. Now the cost aspect is again extremely important to consider. As I just mentioned one or two slides earlier, is that lower time required to optimize the design. What used to take 1 hour maybe takes five minutes now with the help of knowledge-based engineering integrated with AI. So fewer steps means lower cost. So that's the message in the box, is that you got to be highly safe, got to have very high safety standards. Your parts for aeronautical applications, for oil and gas applications, for automotive applications, your parts have to be highly safe, have to keep the occupants safe. They have to be highly reliable, which means to say 5,000 cycles, 8,000 cycles of continuous usage is the minimum requirement. At the same time, keep the cost down. How do we get all of this? Is through AI-based KBE. It's not the magic wand, but it's one of the very key important tools. The other really important, like from my experience working with these tools, what I've noticed, what I have learned, it is that there are so many standards in the automotive field. We have the FMVSS safety standards for the North American market. We have the ECE standards for the European market. Very similar. Asia has its own automotive safety regulatory standards. These standards are so exhaustive. We don't really, the end user should not really have to spend time going through these standards in a very exhaustive, in a very monotonous manner. What would really help if these standards are all automated in a package, and the package just lets you know whether your components or your design is meeting those standards or not. That is where KBE ensures adherence to regulatory constraints. And for this exact reason, one of the examples you will see in the further slide, one of the examples that I'm going to show you is regarding the FMVSS standard tool that I had worked on and how it has helped. So coming to the first real world example that we're going to talk about, and this is from a very recent experience, is the predictive failure pattern detection. And it's very important to recognize the part failure or how the part is doing in the field as early as we can. You know, in the automotive field, I'm quite sure most of the folks here have worked with automotive suppliers or with OEMs. You know, the first 3 months in the service of a particular vehicle is highly important, because that really shows how your vehicle, how well engineered the vehicle is, because the first 3 months is going to be a make or break. A lot of times when we have very high first 3 months in service warranty trend for certain components, it means that part is not going to last long, because if only 3 months of field usage has kind of worn out the component, I don't expect it to last long. So that's going to be a huge, big warranty bill for the company. So the earlier that we come to know, is it could really help looking at the root cause. It could really help as to recognizing the trend. You know, is the part failing in a certain geographical region only? Is the part failing in low temperature or high temperature or in arid regions? Is a part failing in mountainous regions? So what is it? So all of these different complicated weather, geographical, and the driving conditions can be analyzed through AI, because it is AI systems, because of the capacity, can do millions of calculations in 1 second. So the number of inputs can be multiple, which if you can imagine, if these inputs are to be studied and to be analyzed by a human, I'm not saying it's not going to happen, but it just takes longer time, and which is what we want. We want faster output, and we want the output to be helpful to the company. So looking at historical warranty, every single day when the claims are fed, the AI systems that are integrated can analyze in real time all of these warranty trends and give very key outputs to the engineers who are working on the line. If the plant engineers who are working, if the quality engineers on the line get the inputs, then the modifications can be done, so that the vehicles that have not yet rolled out of the line can be fixed, and we fix the problem as soon as we hear about it. So that is one of the key real life examples that is actually being implemented. There are a lot of companies that are using AI to look at warranty trends. Now, the second real world example, and this is like really it's a very interesting application, and I had extensively worked on it, and it was very satisfying to see how the output can be so optimized. Uh, so basically, if you look at different vehicles, especially seats and especially components that the end user, like a person who drives a car, is mainly interacts with the seat, and he also interacts with the instruments in front of him, which is a steering and which is the instrument panel. So ECE and even FMVSs have certain zones which are defined as the head impact zones, which are the zones which are most likely the occupant is going to impact in case of an accident. So there is a similar zone for the side impact. There's a similar zone for the rear impact. There is a zone for the frontal impact. So these are all regulatory standards which are time consuming. Back when I was at Magna Seating, we used to spend quite some time looking at what is the head impact zone for a frontal impact, and making sure that none of the components in that head impact zone have any sharp edges, because sharp edges, as you know, can lead to serious injury, and even the occupant might die. So if all of this regulatory standards are integrated in a CAD tool, and as soon as you're designing the instrument panel, or as soon as you're designing the seat systems, the tool, the software can immediately warn you as soon as your design is not meeting the standard. That will be like a magic tool. It's like a game changer, because you don't have to design everything and then look for the FM and then see if it meets the standards or not. It sounds easier than done, but there have been so many instances. I don't remember a single seating program that we have worked on where modifications need not have been done had it met the FMVSS standards. So the time required to optimize the parts is really short. And as I was mentioning, at Infosys Consulting, I was a part of. We had made this tool using very fundamental Visual Basic script that ran in a CAD environment. And if you feed the instrument panel CAD, it would identify the zones, and it would identify the edges that were not meeting your FMVSS standard. So, this was way back in 2011-12 timeframe. It was a 40-hour job for a set of two engineers to completely comb through all the instrument panel CAD, and then look at all the edges which were not meeting the standard. With the help of this tool, it depends on the quality of your CAD software, but even worst case, it had optimized the design effort to less than 2.5 hours. So a 40-hour job was being reduced to something like 2 to 2.5 hours. And the AI can then use the real-time safety data and see what else can be optimized, how else can we design and optimize using the latest failure trends. The application is infinite. It's you can think of all kinds of regulatory and math and physics that can be um, clubbed into a simple tool which can do the job. We're coming to the very end. I think I'm right on time. Is basically what we have seen so far is a very high-level view of what is KBE and what is AI. One of the fundamental issues that we face is, if you go back to the very first computing rule, is that garbage in and garbage out. So AI mainly depends on what you feed. If the data that is used to train the AI systems is not a robust data, if it's not representative of the failure mode, then the output you're going to get is also going to be not appropriate, because AI basically is just going to use what you have fed. So it again goes back to the engineer to validate what you're feeding into the AI tools. And integrating with the existing systems is a huge challenge, because AI is a very new technology, and most of the tools that we have are extremely legacy based. So one of the challenges that we have really faced is that not all the AI tools are kind of compatible, and they don't really work as expected. So there are workarounds, but it's not seamless as we would think. And the biggest uh, the biggest obstacle is that the change culture. Teams do not really don't like to integrate something new. If it's a legacy based system and if it's been working so fine, then why do we have to change it? So there is a lot of assistance, and the change culture is where we struggle, and also upskilling the teams to kind of look at AI more as a companion, more as a friend, and more as a tool that can be used to enhance and to really fix the gaps that we have right now. Key takeaways, I would say, just summarizing it, is that it builds a very proactive culture of safety through reliability. It can in a very fundamental level, it can greatly enhance safety and reliability from all the points that we just mentioned. It's faster decision making much earlier. The faster we find out, the better it is, and it reduces the time and the steps required to reach the final optimized output. I think we have pretty much come to the end, and thank you all for um, this opportunity. Thank you, Don. Thank you for reaching out, and um, my email is mentioned here. Please email me any feedback that you have or any questions. I can give you much better, much larger examples where we have used ABE to enhance the systems. And please reach out. And with that, it's back to you, Don. I'm looking forward to any questions from the team.
There were some questions about specifically you were talking about warranty inputs and
Yeah.
problem solving from warranty. What kind of are you talking about knowledge-based engineering and AI? Are you feeding an AI chatbot or something, or do you have apps, or what's the
Yeah.
physicality of getting data
Yeah.
into the
It could.
model?
So yeah, it could be chatbots. It could. So again, every company has its own AI-based systems. Some companies have chatbots. So what I meant was not really a chatbot, but what I meant was mainly a kind of a. If you look at knowledge-based engineering application, something that filters out the key points from claims. So when I have hundreds of claims, there is so much of data, and there is so many inputs that go into the root cause. So I think just scanning through these inputs and skimming through and really identifying what are the key input parameters that affect the output. Like if you look at the y equal to mx plus c, output is a function of the input. So what are those real inputs? A lot of times when we when we engineer a part, there are so many complicated inputs. It could be hundreds of inputs um, that go into that can help root cause, but just because of the scale of our systems, we focus on a few of them. So KBE and AI can help look at those inputs and filter out and clean up the data and give you a much better control as to what are the root causes that can help design the optimized part.
I have a question. Do you have any top most important suggestions on how to get started implementing AI with reliability data? First steps.
First steps.
Hello? Did we lose Kartik? Ooh. I believe we lost our presenter.
Yeah, our panelists have dropped down from 8 to 7.
Yeah, and that the most important one. So um yeah, I had some other questions offline. People were asking about, what does this physically look like? A lot of us are talking about we've used like a chat GPT to ask, and I'm pretty awed with the answers you get out of some just broad-based questions. But I'm sitting here thinking of the stuff that I used to do back in the older days. I would get build month, claim month. I would get warranty data by region, by miles, and depending on the mechanism we were looking for, we'd look at it, high corrosion, low corrosion. I mean, there were all kinds of physical things you do just with your eyes and with Excel maps and things. But I'd really like to see an example of how that works with AI, an AI application. I am not seeing Kartik come back. I've only got 6:51, so we've got a little bit to go till 7. So let me see if I can text him and find out.
Or at least email them what questions, maybe he could get back with us.
Yeah, we might do that. The recording saves the chat questions, and we'll see if we can maybe get an example wrapped back. I'm 99% sure we didn't do anything to kick him off because we are all still here.
Yeah, he left abruptly, so it must be something like that.
Kick the plug out. Okay, I've got his presentation here. Let me see. Um, yeah, I've got his email from Ford. I don't know what she's monitoring. The guys, I don't have his phone number to text him. I'll do like the text to his Gmail and see if that works. That's not him. Okay. I think we're gonna have to call it. We still have 36 people on 29 attendees and then the 7 panelists, but we lost our man. So, yeah,
How
this was
many
kind of,
slides were left? Don,
what's
how
that?
many slides were left? You
He
have
was
his
done.
presentation.
He was
Oh,
done with the presentation. He was taking questions. That's where we were. And there were a couple questions coming in about, what does this physically look like? What kind of data, and I had some specifics about warranty problems about how that would work because, Jay Zhao's on and he and we used to do that stuff for a living. We'd look at the field returns coming back and if there was a way to assess like infant mortality data and project what reliability might end up being like, that would be so fun to know about, but I think we're kind of not able to do
oh
that
yeah.
right.
So maybe we can get answered via email and then I can
Yeah,
send
yeah,
those
we'll see if
answer
we can
to
do that.
members who ask
Um,
those questions.
Okay, so in the chat, I had the question from Ted Whalen, which I will pass on. There's Kartik, he's back.
Yes.
Hey Don,
Hey, there you are.
I don't know what happened. It just
Yeah,
suddenly stopped. I just don't know.
you blinked off. Well, yeah, we've got it's 6:56, so we got a few minutes to go, but we were having some questions about, and I don't know, you probably packed a lot of information into your short time that we gave you, but people were asking about what does it physically look like when we take in warranty data and use KBE or an AI tool to try and sift through it. And I was talking about the fact that, we would get field returns for the first 3 months of a new model, and it would be from all 50 states and some overseas feedback, and you'd have to try and look through and see geographically where the warranty was coming from and whether there might be environmental effects, but it was all manual. So I don't know if you've got a way to describe that in so many words.
Yeah. So what uh, what I can visualize is basically if me as an engineer, I'm working on a certain component, and if there have been failure modes with that component in the past model years or in the past for the same model year, but the engineer is not yet uh, completely aware of the root causes. As soon as the component is being designed or being modified, the the KB system can read through hundreds and thousands of claims and look and try to suggest enhancements to the design that can decrease the warranty, decrease the failure, or what you say, decrease the failure modes in the field. One very simple example, and as I was talking, that's the first thing which came to my mind, and I think we just have two more minutes, so I'll just quickly try to explain it. Is that we had created a tool in Magna Seating, which what the tool would do is when engineers or designers are creating certain plastic components, one of the biggest problems that we always face is because of the injection molded components. There are a lot of sink marks. There are a lot of issues with respect to strengthening. Plastic components are, they keep failing. They keep breaking apart. The the attachments keep breaking apart. So all of this can be summarized. The KB tool, the AI can take the warranty trend data, see what's the predictive analytics, what's the future trend, what the KB system can do is summarize the top failure modes and kind of integrate it and make it into design rules, top 3 design rules with which can decrease your uh, failure modes by 80%. And then those design rules can be constantly checked and rechecked in real time when the component is being made in CAD. We had a rib checker, a plastic rib checker, and it was doing the same thing. It would just keep analyzing the CAD as soon as your ribs or as soon as certain aspects of the plastic part would not meet the design requirements, it would immediately flag. So visualize it. I mean, that's the best I can explain is like you have the component in front of you on the CAD system, but where the AI and the KBE is doing is trying to see what future failure modes can be prevented by better optimization. I just hope I have answered, and if there's more, then please email me and I can probably answer you in a much more longer, like in a much more detailed manner.
Okay. Yeah, we had a question about, for instance, what do you do when AI and KBE contradict the engineering analysis? So,
Oh, that's a great question, and it's a very real time situation. Is like that's why it's garbage in and garbage out. So when AI contradicts engineering judgment, I would immediately look at what inputs are being fed, what is the data that is being fed to the AI systems, because it's crunching those numbers, it's skimming through all of those parameters. But if those parameters are not really the root cause or not really relevant to the problem that we're trying to solve, it's very much feasible that what the AI can ask you to do, or it might flag a non-existent issue. It might flag or give you an engineering optimization which may not make sense to you at all. So ultimately, it again goes back to the fundamentals. The engineers have to look at the fundamentals. You cannot put 100% reliability on the AI systems only. You have to look at whether those the predictive steps that AI is asking you to do to like optimize, are they really making sense, and do they really mean good engineering judgment or not?
okay. I might put together a couple of questions based on some chat summary, Kartik, but I appreciate it. It's 7:02. I want to respect your time. For the rest of the crowd here, we have 36 people total still out of the peak of 40. So, Greg, are we going to have an officer volunteer meeting after?
A brief one if necessary, yeah.
Okay. All right. So, do you want to take a 5-minute break or 10-minute break and say 7:10? We'll check back in.
Sounds about
So
right.
yeah, so Don, do I need to be on the call, or
No, sir.
is it
No,
okay?
sir. It's very good. Very good. We appreciate your time. Thank you for volunteering
Thank you.
for this. I know this is a lot of trouble and time out of your evening, so I appreciate it. What I was saying for the other participants, though, Kartik, you don't have to stay, but if you'd like to engage with the section and look at some of the volunteer opportunities or hear what we talk about in the officer volunteer meeting, Greg, what do we do? Maybe 10 or 15 minutes at 7:10, reconvene.
Yeah, that'll be fine.
Okay, so I'll go take a quick break, and at 7:10 we'll reconvene. Whoever's left, people that are in the audience are welcome to stay. Otherwise, have a good evening, and we'll get the RUs and the meeting summary out tomorrow.